Hello guys. So continuing with the where's my coffee? Continuing with the series of examples in virtual work, we're gonna do now a frame. We did trusses, we did beams. Now we're gonna be doing this frame here. Okay. So what is this? What is the frame here? Let's see what is happening. The problem is asking for finding the horizontal and vertical displacement at C. You have the modulus of elasticity, the inertia, the area, modulus of rigidity, or shear modulus. You have the rectangle. That section is a rectangular section, and I just copy this here to save some time. The principle of virtual work, again, I want to say it again. The external work at any point has to be equal to the internal work, or the total work is zero, external minus internal. This is caused by a virtual external load and a real external displacement. And this one here, the small m, for example, is the moment coming from the virtual structure, and this m dl over ei, this part m over ei, is going to be the rotation or the deformation produced by the real forces in this frame. So what is the first step here? First, read the problem. This problem has a part that it looks like stupid, if you will, but you have no idea how many people freak out with that. They start working with the horizontal displacement, which is what you have to do. And in order to do the horizontal displacement, then you have to put a load in the horizontal direction. And then they finish that, and then they don't have to do the time for the vertical displacement. Please read vertical displacement. How this is going to have any vertical displacement at C if this is a roller? The only possibility for that to have a vertical displacement is if the roller collapses. And that's not the case. I mean, you're not supposed that to happen. But you can discuss and say that, at least. So we don't have to worry about vertical displacement, just horizontal displacement. First step, as always, is calculating the reactions. So you're going to have a pin here. You're going to have two reactions, and this one is going to be like that. I only have one horizontal reaction at all. This is a y, this is a x, and this is the total load. I didn't put this distance, but this distance is 10 feet, 10 feet, 10 feet, 10 feet. There you go, 10 feet. What is it? What is 10 feet? 5 guys in a row, or 5 girls in a row. What I was saying, okay, good. So 4 times 10, 4 times 10, summation of forces in x, meaning this force here should be 40. Keep. And now you can do summation of moments if you want to here, and then you're gonna say that this force of 40 somewhere over there multiplied by the distance, which is 5, is 2000. 2000 divided by 8, 2000 divided by 8, you're talking about 25 and 25. 25 and 25, keep. And start looking at things like that. I mean, there's a couple, only a couple here vertical that can oppose to that moment. This couple is 25 times 8, and this is 2000, so there you go. Reactions are calculated. We don't have to discuss anything else. Now, what is the next step? The next step is, now this is the real structure, and that's how it's called, real structure. Now we're gonna call a virtual structure, which is gonna replicate the same geometry as the real structure. The only thing that is gonna change is that because we are looking for a horizontal displacement at C, and this is the point C, then we're gonna put a horizontal load there, unit load, a virtual load. And remember, I put 1, but that's 1 keep in reality, because we are doing that. Now, what is the next step? The next step, as in the other case, is calculating the reactions. So let's calculate the reactions. How much has to be the reaction here? Let me put it in green. Why green? Because I never use green, or barely use green. So this reaction here, if this is 1, this is going to be 1 also in this direction, summation of forces in x. And now you have this force here, same thing as before, and this force here. You have 1 times 10, 1 times 10 is 10, and then this is going to be this couple here divided by 8, so it's going to be 1.25 and 1.25. You don't wanna do it like that. It's okay, don't do it like that. Then do summation of forces in x equals 0. 1 minus ax equals 0, ax equals 1. Summation of moments at A. So you have 1 times 10 is 10, right? 10 divided by plus or minus. This is minus plus cy multiplied by 8 equals 0. 10 divided by 8, 1.25. Summation of forces in y equals 0. cy plus ay or minus ay in this case equals 0. Ay equals 1.25. And we have the reactions. Once we have the reactions, the next step is for us to create the functions and the sections that are going to define completely the frames and the system that we have here. So I'm going to make a section here, 1, 1, and I'm going to look at the x from this direction. And yes, I have to do another section here to define the two areas that I have. Now, the thing is, instead of me going in this direction, I'm going to measure my x in this direction because it's going to be way shorter to do that. And we're going to do the same thing here, section 1, 1, for the virtual. And this is going to be x, and you can call it x1, x2, x3. You can call it Pepe if you want to. Any name that you want. 2, 2. Okay, there you go. And those are going to be the sections that we are going to be working. So let's start with this, with the real structure. For the real structure's the easy way. Well, it's statics, but it's okay. Now, I replicate this thing here. This is what I have. The load, 4 kg per foot, like that. I have this force here of 25, this force here of 40, which are the reactions. The distance is x. I always try to follow my coordinate system, the local coordinate system in this way. I always do this xy, and then I go here and I go xy, and then I go, if I have another leg here, and then I go xy. And depending on that, I have to be consistent during the whole problem. So I have that part over there, and if I follow, as I said, this system, then that means that I could do something like this if I want to. And then I can put my moment here and my shear here, because those are the positive accepted conventions, and of course the normal is going to be here. Now, we have all of that. We don't have torsion. But for this particular problem, even though I know that this is going to be the one that it really matters for everything, I'm going to do this, this, and that to show you the minimum effect of these two. So next time that you do something regarding this, you can have more criteria and eliminate things if you don't have to take them. Or if this is a multiple choice FE or PE exam, for example, then you do the moment only. Even SE, you do the moment only, and it's going to be really close to that value. You don't have to do the others. What is our objective? Calculate this big N, this V, and this force. Summation of forces in the x direction, in this direction. This is the x direction for me. So you have negative 25 plus N equals 0, N equals 25. That is for the real structure. Let me copy here real structure. Now this is for the axial. That's what we did, axial. Now let's go for the shear. If it's for the shear, then I do summation of forces in y, meaning this is y, this direction. You can flip it if you want to. Then what do you have? You have, I don't know in what direction you're going, but you can say that you have 40 minus 4x minus v equals 0, and then v is going to be equal to 40 minus 4x. There you go. And now we do the moment for the same one, moment. And for the moment, you're gonna do summation of moments at this point. If you do summation of moments at that point, and I call that point before A prime, you can call it A prime if you want to. You can say this is A prime. Summation of moments at A prime equals 0, like that. So I'm gonna do here, and then you have moment M A prime M A prime, which is this one, and then you have this force, which is 4x. Remember the force coming from this thing here. This is 4 times x, and the distance from here to here of that location is gonna be half of that distance, half x. So you're gonna have ma prime plus 4x multiplied by x divided by 2, and then you have the shear here minus 40, well, the shear depending on what axis, yes, shear, negative 40 times x equals 0. And then you can have your moment A prime, which is 40x minus 2x squared. There you go, boom, moment, done. Now we should repeat the same thing for the virtual. Let's work the virtual here. Virtual, there you go. The virtual is this one. So I'm gonna work the virtual here for the first section. What do you have for the first section? You have this value here, 1.25, this value here, 1, and one section, 1, well, I did it here. So let's put the section here at this point. This distance is gonna be x, and at this end, you are going to have small n, small v, and your small m. And you do the same thing. Now you do the summation of forces in x equals 0. If you do that, then you get that n equals 1.25. N equals 1.25. Summation of forces in y equals 0. And you can put here if you want to. This is the axial. Now this is the shear. For the shear, what do you have? V equals 1. And for the moment, if you do summation of moments at this point, which we called before A prime, then you have that m, positive m minus 1 times x equals 0, so m equals x. There you go, there you go, there you go. And this is the moment. The moment for the virtual. Now we're gonna repeat the same thing for the other member. Now let's work virtual. Now let's work with this member now. If I work with that member over there, and I'm going to measure it in this, in this direction. So basically what you have, this is your roller, and this is the force of 25, keep, and this is the member. This is the section that we did, section 2.2, and another thing that I like to do, and I didn't do it, is that I like to put here, section 1.1, and I have to put from 0 to 10, because that's gonna help me later on. So the same thing here, then I'm gonna put section 2.2, section 2.2, and x is gonna go from 0 to 8, 0 to 8, section 2.2 from 0 to 8. Now we have this. What do we do now? This part, I have to use the same convention, right, that I was using before. So if I use that convention, because I'm coming from this side, I have to use this this part of the beam, like that. And this distance is gonna be x. Okay, good. Now what do we do? Summation of forces axial. Summation of forces in x equals 0. N equals 0. Shear. Summation of forces in y equals 0. V equals 25. V equals negative 25. Plus V plus 25 equals 0. V equals negative 25. Summation of moments at this point, which T C prime, I don't know, C prime, summation of moments at C prime, M minus 25x equals 0, M equals 25x. Done. No nonsense. Double negative, you see, no nonsense. Now let's do this is the real once again. Let's do the virtual. If I'm gonna do the virtual, where are you, virtual? Virtual is this. Virtual. This is the virtual now. This part. So if I'm going to do that, then let's do it. Let me put here the same thing. The roller, this force 1.25. This force, which is the one that is we put for the virtual displacement. I don't know what I'm gonna put units if I didn't put the units before. This distance, x, the other side of the beam, convention. That sounds like location. Well, here is convention. And this is the virtual part. Same thing, summation of forces in x, n equals 1, axial. Shear, summation of forces in y, v plus 1.25 equals 0, v equals negative 1.25. Moment, and this is the point C prime, summation of moments at C prime. Then you have 1.25x minus m, so m equals 1.25x. Second page, done. Now I want to calculate separate the contribution of each one of the cases. So let's start with the biggest one, just for the sake to show that it's big, and let's talk about the contribution of the moment to that displacement. Contribution of moments, meaning summation of mm over ei dl. That's what we want to do here for this contribution of the moment. Okay, E is constant, I is constant. I can take them out of the integral, out of this part, and put it outside. So that's what I'm gonna do. It's gonna be 1 divided by EI. That is gonna multiply. First, let's talk about this leg. This is the real, this is the virtual. So what is the real? The real is, for the moment, is this one. 40x minus 2x squared, and the other moment, the virtual moment, is x. So multiply by x dx, integral of this, between what and what? Between 0 and 10. That's what I put this part here, between 0 and 10. Now plus the integral of, now the second part, moment 25x, moment 1.25x, 25x times 1.25x, from 0 to 8, from 0 to 8, 0 to 8 dx. Now you can solve these by parts, you can solve whatever you want to do, and then you can evaluate it. I know your calculators do that. If you want to just do it for the sake of doing it, you can say 40x times x is going to be 40x squared. When you integrate that, it's going to be 40x to the third divided by 3 minus 2x to the third. That means 2x to the 4 divided by 4. And this is from 0 to 10. This part evaluated from 0 to 10. 1 over EI is constant. Plus this part, which is just 25 times 1.25 is 31.25. 31.25 x squared means x to the third divided by 3 from 0 to 8. Important thing here, and now you put 10 here. I'm gonna do it just for this one. I'm not gonna do it for the axial and for the shear. But then you put here 1 divided by EI 40. Some people hate this, some people like me doing this, so I don't care. You should make a poll. Do you hate it or you like it? And this is from this is already this part plus this other part, which is a 31.25 times 8 to the third divided by 3. And once you do that, the only thing that we have to do here, remember we multiply this by this 1 over EI, so you put it here 1 over EI. E was 29,000 KSI and the area was 600 inches to the fourth. Remember, I showed you in the previous video that to keep the units coherent, because we're working with inches and we're working with feet, and we're working with the moment. If you put all the units together here of everything that we are doing, at the end we have to convert cubic feet into cubic inches. So that means that this has to be multiplied by 12 to the third, just for accounting for that. Cubic feet to cubic inches. And the result, of course, is going to be the displacement. And this displacement at the point C induced by the moment. And that value is going to be 1.357, minus 357 inches. There you go. Contribution of the moment. And I'm going to call this page 3. Now, let's work the contribution for the shear or the axial. Let's do the contribution of the axial because I have it here. Contribution of axial. It's the same thing. We just take the same 1 times delta due to the axial, and that's going to be the summation of the integrals of n over AE multiplied by the L. Once we start doing that, this is going to be equal. Area is constant, E is constant. You take it out of the summation, and then you start real, normal, 25, real, virtual, 1.25, normal. So it's going to be the integral of 25 times 1.25 dx from 0 to 10, plus the integral of, oh look at that, 0 times whatever, 1 dx from 0 to 8. This is going to be 0, and of course this has to be multiplied by 1 divided by AE, and then 1 times delta, or delta if you will, is going to be equal that this is 31.25x from 0 to 10, which is equal to 31.25 times 10, but we have to multiply this by 1 divided by AE, so this is going to be divided by AE. A is 80, A is 80, A is 80 and E is 29,000. And once again, if you work out the units here, you're gonna end with feet. So I want to convert this into inches, to convert feet into inches. And the contribution of the displacement, horizontal displacement at the point C due to the axial, is prepared to be amazed by this great contribution. 0.0162 inches. Wow! I'm so happy that we didn't have to work that much, because if I have to work 4 pages to get that number, I will rip it up right now in pieces. Now, fourth contribution of the shear towards the big picture. Contribution of the shear towards the big picture. Now, once again, the displacement due to the shear is going to be the summation of all the integrals of kV and V times V divided by GA times the L. And this KB, remember, it was a fear factor. It was a form factor, which for rectangular sections, it was KB was 1.2. Do I have to know that? Well, I only know rectangular, circular, and W beam. 1.2, 0.9, and 1. But there is a way, then there's tabulated, and there are formulas also. Okay, anyway. So let's do that. We already have everything else. So let's do that. This is going to be equal to K is constant because everything is constant, G is constant, A is constant. So I'm going to put it here outside the integral K, G, A, and everything is going to be multiplied by the integral of first part from 0 to 10. What is the shear? 40 minus 4x. 40 minus 4x. This is the real. What about here? Virtual. 1. I like that. No multiplication of x's. You know, when you have several x's, life is complicated, I was being told. Plus integral shear 25, shear 1.25, dx 0 to 8. Put this, evaluate that, and this is gonna be 40x minus 2x squared from 0 to 10 plus 31.25 x from 0 to 8, everything multiplied by k divided by g and area, and at the end the units here are going to be in feet, so I have to convert this into inches, so I multiply that by 12. Remember, you can prove that. You can just put all of the units here and see what you're getting, and you will realize that this is the multiplication, because this is, if I want this in inches, then this is going to be keep, for example, keep, and this is going to be keep over square inch, and this is going to be a square inch. Inch and inch cancel, keep and keep cancel. This is keep, this is keep, so there's only one dimension of units here that I have to multiply by 12. Remember, conversion to feet to inches. And once again, we put all that together. We put the tens wherever the tens goes. We put the 8 wherever the 8 goes. We totalize that, and we get an amazing contribution for the shear. At the point C, displacement, horizontal displacement due to shear. Point C of 0.00675 inches, and give the shear a hand. Yeah! Now if you put all together, the total displacement, horizontal displacement due to everything, is going to be total horizontal due to all the effects is going to be 1.357 inches due to moment, plus 0.00162 inches due to axial, plus 0.00675 inches due to shear. Total horizontal displacement equals 1.365 inches. Compare that with 1.36, 1.37 inches, 1.36 inches. It's the same thing, same difference, like my son said. So, does it worth it? Well, it's worth it if I tell you in one exam, oh, these are 10 points for doing this, and if you don't do it, of course it's worth it because you lost 10 points. But in real life, for that type of values, it doesn't worth it. Anyway, anything now is calculated with software, and you don't have to worry about that. But I just wanted to demonstrate you what happened and how to be let's say, at peace or at ease when you are dealing with a problem if you don't do that part. See you later, guys. Keep watching and keep learning.